All right, good morning to you all. Welcome back to our control system theory classes. Today we're going to talk about, in general, different properties of Laplace transform, and we are also going to introduce inverse Laplace transform. Okay, and we're going to learn a few things about inverse Laplace transform and how we actually use Laplace transform in conjunction with inverse Laplace transform for in control system engineering. Okay, so this is going to be the objective of our class today. And as usual, during the class, if you have any query, make sure to ask your questions here on the chat, and I'll definitely answer your questions. All right. So, with that being said, I believe, of course, we talked a little bit about Laplace transform, and I believe you had a complete discussion, full discussion on Laplace transform. So many. Just hold on for a second. All right. So as I was saying, we talked about Laplace transform a bit, and then we, of course, you of course had a class on Laplace transform in general, your mathematics classes. So we of course know a little bit of Laplace transform, but we are going to introduce a few more things and a few things that you already knew. All right. So that's going to be the structure in today's discussion. All right. But keep in mind that we introduced Laplace transform as an extension of Fourier transform. Okay, so this was kind of a generalization of Fourier transform, and because Fourier transform in by default is not applicable to many functions, many different functions which do not satisfy the Dirichlet conditions. Okay, the Dirichlet conditions. So the signals must satisfy the Dirichlet conditions first in order for them to have a Fourier transform. Okay, so in order for that integral to actually converge. And then we actually boiled it down to the absolute integrability of the function. So essentially the signal of the function that you have, if you want to calculate a Fourier transform, the Fourier transform is guaranteed convergence if the function is absolutely integrable. Okay, so again we saw that there are many common standard functions like the ramp function, for example. It is not absolutely integrable, and as such its Fourier transform does not exist in the standard sense, for example. Okay, and then we realized that if we have the Laplace transform, we can actually replace s with j omega to obtain the Fourier transform, not for s equal to 0, not for omega 0, but for every other value. Okay, we actually figured that out. So there are a few things we're going to revisit today during that in part of that discussion, and we are going to actually once again define Laplace transform. Start by defining Laplace transform as an extension of Fourier transform. We know that Laplace transform of a signal xt is defined as an extension of the Fourier transform of that same signal, and that extension is essentially talking about the Fourier transform of xt times e to the power minus sigma t, where sigma is the real quantity, sigma is the real number. Okay, sigma is the real quantity, and essentially we multiply the signal with a damping term here. So this term is supposed to be a damping term, which not damping term, sorry, decaying term. So this term actually decays this signal so that this total thing is guaranteed absolute integrability. Okay, and as such it has a Fourier transform, and as such we define Laplace transform as this. Okay, so this was kind of the definition of Laplace transform, and then of course from there we derived that yes, essentially Laplace transform is denoted as xs, which is nothing but x sigma plus j omega. Okay, so this was sort of like that. So this was the discussion we had. Okay, so Laplace transform is nothing but that. So this is essentially coming from the concept of Fourier transform. So we introduced this earlier. Okay, so we said that Laplace transform was an extension of Fourier transform. Laplace transform as an extension of classical Fourier transform. All right, so we actually did that. I hope it's understandable. right? And then of course we derived a few expressions, like we calculated the Laplace transform for a few things. Okay, and just to again remind you that this sigma is based on our choice, so we can choose a suitable value for sigma such that the convergence of this entire thing is guaranteed. Okay, so that the Fourier transform actually exists of this thing, so that the Laplace transform exists. So again, Laplace transform does not always converge by default. You have to choose a suitable value for that. So that's called the region of convergence or the condition on convergence. And we actually kind of skipped that part. We discussed a bit of it, but we actually skipped that part. And I said that we are not going to discuss convergence of Laplace transform in totality. Okay, so that was it. And again, we defined Laplace transform of a signal as this integration. So that was 0. So that was, sorry, this was the correct definition. So from minus infinity to plus infinity, and that would be xt e to the power minus st dt. Okay, so ultimately we figured that out. Okay, this was essentially e to the power minus sigma t times e to the power minus j omega t, and of course from there, right, we actually derived that this is the definition of Laplace transform, and this is quite obvious, right? This is the definition of Laplace transform, and we actually once again we discussed all these things in our earlier classes. So the totality of this was discussed. Not a problem, I hope. Right? With that being said, let's say that once again during this discussion, feel free to ask questions that you might have. Okay, so this is what we are defining Laplace transform. But again, where did this come from? This came from the concept of Fourier transform, right? So this is again the Fourier transform of xt times e to the power minus sigma t. Okay, and that would have been this integration xt. So let me shift this a bit. So xt times e to the power minus sigma t times e to the power minus j omega t dt. Of course, we are calculating the Fourier transform of this. So this is what you do usually. Right? So that is what is done here as well. So that's equal to this because we write it in that form. So essentially, if we write this as minus sigma plus j omega t dt, and we instead of writing sigma plus j omega, if we just write s, that is exactly what we get essentially. Okay, so this is equal to, by definition, minus sigma minus infinity to infinity xt e to the power minus xt dt, where we are assuming that sigma plus j omega to be s. We're just replacing this variable. Okay, so that's again how we define Laplace transform. Now with that being said, let's think about how we can actually figure out inverse Laplace transform, how we can actually think about inverse Laplace transform. But let me recall that we defined, or rather we derived the expression for inverse Fourier transform in our signals and systems classes. All right, we defined inverse Fourier transform, and since we are defining Laplace transform as nothing but an extension of Fourier transform, then it is only logical to assume that inverse Laplace transform is nothing but an extension of inverse Fourier transform, right? Since we are defining Laplace transform as an extension of Fourier transform, then it is only logical to assume that inverse Laplace transform is an extension of Fourier transform. And that is exactly how we are going to approach the problem here. Let me remind you once again that this is how we define Laplace transform. Okay, so this is the definition of Laplace transform that we have been using. All right, so we are saying that the Laplace transform of a signal, which is xs, okay, is defined as the Fourier transform of xt times e to the power minus sigma t. Okay, all right, once again minus sigma t is there, e to the power minus sigma t is there to actually make this entire thing converging, right? All right, so as such, we can actually once again, instead of writing s, we can write sigma plus j omega. So this is this, okay, and this is going to be something like the Fourier transform of this xt times e to the power minus sigma t. Okay, all right, we can say that. And because of this very definition, we can now say that xt, that now that we can say that the inverse Fourier transform applied on this signal, sigma x sigma plus j omega, whatever that is going to be equal to xt times e to the power minus sigma t. Isn't that right? So this is the Fourier transform of something, okay, and this is that something. Now, of course, the inverse Fourier transform of this will give you the original thing on which you took the Fourier transform, right? So that is what we have written here, right? So let's just change the sides here. So we have xt times e to the power minus sigma t. So try to understand once again, our goal is to figure out a definition for inverse Laplace transform, and that is going to be inverse Fourier transform, obviously, of this x sigma plus j omega. But we defined inverse Fourier transform, or rather we derived the expression for inverse Fourier transform, the formula for inverse Fourier transform, in our signals and systems classes. We know that by definition inverse Fourier transform is this. Let me just once again write it here. That by definition inverse Fourier transform, just bear with me for a second. So many things are happening since morning. Okay, people are clapping outside, and then trucks are going, I don't know. Alright, so this is the definition of inverse Fourier transform. Let's apply that. This is from minus infinity to infinity. So this is whatever we have here. We multiply that with e to the power j omega t and integrate with respect to omega. That's exactly the definition of inverse Fourier transform. Let me add a few more pages. Okay, let me save this. All right. So this is the definition of inverse Fourier transform. So we are always definitely happy with this. Not a very difficult thing to understand, I hope. Okay. So let's write it. So this is xt e to the power minus sigma t. We are familiar with the expression in the right hand side, right? So this is the very expression for inverse Fourier transform. Now notice that in the inverse Fourier transform, we are integrating with respect to omega, and that's obvious, right? But there is just one more thing I need to mention, that here we are using the full definition of Laplace transform. Okay, we are using the full definition of Laplace transform. This is the full definition of Laplace transform. So integrating from infinity, minus infinity to plus infinity. Okay, so if xt is causal, then we integrate from 0 to infinity. Okay, but we are not assuming any particular condition, because what we are going to derive right now is applicable for any signal, or rather will be applicable for any signal. Okay, just keep that in mind. So now that's the thing. Now here we are integrating with respect to omega. So anything that is not a function of omega can be treated as a constant. So what I can do, I can write xt here and bring this e to the power minus sigma t to the right hand side. So I can divide both sides with e to the power minus sigma t. So essentially I am multiplying with e to the power sigma t. So I have 1 by 2 pi times e to the power sigma t and this integration. This is going to be x sigma plus j omega e to the power j omega t d omega. Now once again notice that this thing is completely free of any variable omega, right? Completely free of the variable omega. So as far as this integration is concerned, this is a constant. Okay, as far as this integration is concerned, that's a constant. Okay, because this is not a function of omega, because we are integrating with respect to omega. That's the obvious thing, right? So what you can do, we can actually bring this inside the integration and nothing will change. Okay, the result of this whole expression will not change, and that's exactly what we are going to do. So we are saying that xt is equal to 1 by 2 pi integration from negative infinity to positive infinity, and we have x sigma plus j omega. Of course, we're just doing scalar multiplication, so order is not important. Sigma, and then we have e to the power sigma times e to the power j omega t d omega, and obviously these two can be combined, you can see. Okay, and we can write it as e to the power sigma plus j omega t. That's obvious, right? So since this is irrespective of omega, that can actually go inside, and we are writing it that way. Okay, and now let's do a trivial let's do a substitution. Okay, we are going to integrate, do a substitution in this integration. Okay, and what kind of substitution? We know, because we assume sigma plus j omega as s. Right? That's the substitution we'll do. So let's do that substitution. So let's assume that sigma plus j omega as s. because that's exactly the substitution we do. Now, of course, if we take the differentials, sigma is irrespective of omega, so that's again becoming 0, and then we have j d omega equal to ds. Those are the differentials. All right. So we write d omega, that's going to be 1 by j ds. J is once again complex unity. So instead of d omega, I will be writing 1 by j ds. That's not a problem. Now we have to think about the limits. Okay. Now let's say, so we originally had the limits on omega, and now we are going to have limits on s, right? Now, of course, omega varied from negative infinity to positive infinity in the original integration. Now, when, say, omega is negative infinity here, what is the value of s? When omega is negative infinity, you see that we have sigma minus j infinity. You notice this very carefully. The result is sigma minus j infinity, because you see that whatever value of sigma I have here, that's only changing the imaginary part of this complex number. S is a complex number. Whatever value of sigma omega I have is only changing the imaginary part. It is not affecting the real part. So we would say that the value of s starts from sigma minus j infinity, and when this omega is infinity, I put infinity here essentially, and this is sigma plus j infinity. So the limits are like this, sigma plus j infinity. Okay. It's like that. So keep that in mind, because this is going to be the limit. These are the modified limits that we're going to put in this. Okay. So now, with that being said, we can now say 1 by 2 pi integration whatever. So here I have x, I am writing s because we assume sigma to be sigma plus j omega to be s, and then we have e to the power st, and instead of d omega I would have 1 by j ds. So 1 by j and ds, and of course 1 by j is a constant, it can actually go outside, so it can become 1 by 2 pi j, and this is becoming ds. And what about the limits? The limits are from sigma minus j infinity to sigma plus j infinity. Okay. Sigma minus j infinity to sigma plus j, and that is exactly giving you xt. So starting from the Laplace transform, if you do obtain this integral, what you get is the original signal. So this is the definition of inverse Laplace transform. So this is the definition of inverse Laplace transform. So this is how we define inverse Laplace transform. Now, obvious problem that you can see is that this integration, this very integration in the middle, is not a very real integration. It's a complex integral, right? So we are doing a complex integration here. Okay, complex integration. And can anybody tell me what is this complex integration all about? I mean, what kind of complex integration is this? So there are several different types of complex integrations, right? You see, sigma here is essentially coming from the condition of convergence. Okay, it's coming from the condition of convergence. We actually derived in the previous class that sometimes we need to assume sigma to be a positive quantity. Okay, so something like sigma greater than 0 is for ut, for example. Okay, if we want the Laplace transform of ut to exist, we need to assume sigma to be greater than 0. So condition like that. Okay, so essentially an integration that is happening with that sort of condition. So if you think about the complex plane, if you draw the complex plane here, okay, and let's say sigma is positive, so again it came from the condition, okay, condition of convergence. Okay, sigma is a positive quantity. So what is this integration really talking about? What is this integration really talking about? This integration is really talking about an integration over a certain region. Okay, an complex integration over a certain region. So we say that sigma is positive. Okay, so complex number once again. So this is sigma and this is the omega axis. So this is called the S plane. Okay, so we say sigma is positive, which indicates that we are talking about this entire region to the right. Okay, so in this region all sigma are positive, right? And then we integrate from negative infinity to positive infinity in the omega axis. So essentially we take all positive values of sigma and we integrate from bottom to top. in terms of omega, right? So omega is varying from negative infinity to positive infinity. So in other words, we can say we are integrating with respect to the entire right hand quadrant here, right hand set of quadrants here. So entire right half plane, we call it the right half plane. So we are actually integrating with respect to the entire right half plane. Okay, just to give you some idea. Yeah. So if sigma is positive, so for example, this is sigma greater than 0. Okay, and of course omega is varying from negative infinity to positive. As a similar example, if we find out that this should be the condition for convergence, say for example, if we say sigma should be greater than 1, then we can say that okay, sigma is greater than 1 is actually denoting everything to the right of this, right? To the right of this, because this is again the sigma axis and this is the j omega axis. Okay, and since it is denoting everything to the right of this, and we are integrating from for omega, which is starting from negative infinity to positive infinity, we are actually integrating with respect to for this entire region. So you can understand that this is a complex integration, and complex integration by definition is quite complex. Okay, the way you treat this kind of integration is through something called the Cauchy's residue theorem or Cauchy's integral formula. Okay, so what you do is called the Cauchy's integral formula or the residue integral. You calculate the residue of this function and you actually calculate this. The thing is, we people are engineers, and we, some way or the other, we hate complicated calculations, and so did the engineers who actually applied Laplace transform for system analysis for control systems. Okay, and what happened is that we do not really use this formula directly to calculate inverse Laplace transforms, because that way this thing would be unnecessarily complicated. But later on, if you wish, I can actually show you how to do inverse Laplace transform by directly applying this formula. I'm pretty sure nobody has ever bothered telling you that you can actually calculate inverse Laplace transforms directly by applying this formula. Okay, I'm pretty sure nobody told you that. Okay, rather nobody showed you an example of that. But I can show you a few examples, quite a few examples that can be actually, you can actually do inverse Laplace transform directly by solving this integration. Okay, and this is not a very difficult integration thanks to Cauchy. Okay, so you can use Cauchy's different theorems regarding complex integrations and actually calculate inverse Laplace transforms directly applying this formula. But we don't do this. As engineers, we try to think of inverse Laplace transform as an opposite process of Laplace transform. What do I mean? We mean this. For example, we say that for causal, again, we are assuming causal signals. Okay, otherwise things would be different. So we are assuming all signals to be causal. Under that assumption, just keep in mind that throughout our discussion, since we are not discussing region of convergence for Laplace transform, we are assuming all signals to be causal. Under that, we know that the Laplace transform of ut is 1 by s. So instead of actually so for example, when I ask you, okay, fine, what is the inverse Laplace transform of 1 by s? Actually, instead of calculating all this integration, for example, instead of calculating this integration, instead of actually doing this integration, we are going to actually use the reverse fact. What we are going to say, instead of doing this integration, we are going to say, okay, we know what is this, because we know that the Laplace transform of ut is 1 by s. So definitely the inverse Laplace transform of 1 by s is going to be ut. So we are going to use the knowledge of Laplace transform to calculate the inverse Laplace transforms. But let me once again assure you, you can 100% of the time you can actually calculate the inverse Laplace transform directly using this formula, and this is exactly computer programs too. Okay, so when you ask Python, for example, to calculate inverse Laplace transform, it is easier for the computer program to do it this way. So whenever you're dealing with a computer program which is actually calculating inverse Laplace transforms, it is actually calculating this complex integration instead of figuring out what came from what. Okay, so again, this is usable in a computer program. Okay, also usable analytically, but these are once again the techniques that we use for calculating inverse Laplace transform. So for all intents and purposes in our course, we use inverse Laplace transform as just the reverse process of Laplace transform. Okay, not with this integration, but keep in mind, if somebody asks you what is the definition of inverse Laplace transform, what is the formula for calculating the inverse Laplace transform, this is it. Okay, just keep that in mind. Any questions so far? If you have any question, please ask. Alright, so that being said, we know the Laplace transform of quite a few things, and I would actually leave this as homeworks for you because you can actually figure these out pretty easily. Okay, you can actually directly calculate the integration and calculate the Laplace transform of these few things. We know that the Laplace transform of the impulse signal is 1, that the Laplace transform of e to the power at ut is 1 by s minus a, where a could be a complex number, could be a real number. It does not have to have any condition on that. Okay, we know that the Laplace transform of sine at, and you can once again calculate this pretty easily because sine at is e to the power jat minus e to the power minus jat by 2j, and e to the power jat, and of course e to the power jat is just like e to the power at. Okay, instead of a you have ja, so e to the power jat would have a Laplace transform of 1 by s plus ja. Okay, and that way you can actually calculate this pretty easily, pretty quickly. You know what, let's calculate this. Instead of doing this, let's calculate this. So e to the power sine at ut. Okay, we are making sure that everything is causal here. So we are calculating the Laplace transform of this. So essentially this is equivalent to calculating the Laplace transform of e to the power jat minus e to the power minus jat by 2j times ut. And of course you can see that 1 by 2j is a constant because it is neither a function of t nor a function of s. It does not have anything to do with those, so it's a constant, it can go outside, and we are left with the Laplace transform. We are left with the Laplace transforms of e to the power jat ut and minus Laplace transform of e to the power minus jat ut. Now obviously, even though I didn't tell you maybe or didn't derive, Laplace transform is a linear operation, which means that the Laplace transform of some signal plus some other signal is equal to the sum of their individual Laplace transform, like fs plus gs, and so on and so forth. Constant times here, so that constant comes up here. So essentially Laplace transform is a linear operation. You can again see this by just applying the very definition of Laplace transform, just like we did for Fourier transform. Now of course this is 1 by 2j, and here we know that the Laplace transform of e to the power at ut is 1 by s minus a. So Laplace transform of e to the power jat ut, assume this ja to be something like a, this is going to be 1 by s minus ja, and similarly this is going to be 1 by s plus ja, because this a here is like minus ja, and just like that, if you put minus ja here, you get 1 by s plus ja. And if you simplify this, this becomes 1 by 2j, and then of course we have s square plus a square here. If you take this, multiply them, and here we have s plus ja minus s plus ja. Just subtract them as you usually do. So there s cancels out, and you have 2 ja on top. Okay, 2 ja on top, and here you have s square plus a square, and since you have 1 by 2j here, this 2j will cancel out. So essentially you would have a by s square plus a square. That is what you have for this Laplace transform. So this is a by s square plus a square. You see that we did not integrate anything here. We just used the known Laplace transforms here. Again, these are all known to you. I understand that all of you pretty much know these things, right? But in case you don't know, you can actually follow along right here. So that's the Laplace transform of sine at ut. Similarly, we can calculate the Laplace. Just hold on. This was talking about inverse Laplace. Okay, Laplace transform of cosine at ut is going to be s divided by s square plus a square. Once again, by using the very Euler's formula for cosine at, which will be e to the power jat plus e to the power minus jat by 2. Using that, you can actually see that this is the answer. Okay, so that's once again not a very difficult thing to understand. So that's fine. Okay, a few more things. Laplace transform of hyperbolic functions. Hyperbolic functions like sine, it's called sine hyperbolic t. Now, with ut. Now, what is a hyperbolic function? Let me just write down the definition. I'm not going to go into the details of this. We would need this at later point of time, but not right now. So we're just going to define this. Okay, not t. Did I write t? Not t. Just a. All right. So sine hyperbolic of at. Okay. So this is going to be e to the power at minus e to the power minus at by 2. Notice that there is no complex number here. There is no j or whatsoever. And of course, by using this very definition, you can actually calculate this pretty easily. Okay. This is going to be a by s square minus a square. Okay, so that's sine hyperbolic. Okay. Similarly, the Laplace transform of the hyperbolic cosine at ut. These are again standard functions. So this is going to be s divided by s square minus a square. Once again, by using the definition of this, which is cos hyperbolic at, and that's defined as e to the power at plus e to the power minus at by 2. And using this definition, calculating the individual Laplace transforms and adding them properly, you can actually calculate the Laplace transform there as well. So this is not a very difficult task in any stretch. So not a problem, right? I hope you understand all of this. These are pretty easy to understand. All right. And once again, we derived earlier that the Laplace transform of Laplace transform of TUT, which was the ramp signal, is 1 by s square. Okay, and we can actually generalize this to t to the power n. Okay, so far not a problem for us. Just keep in mind that for let me just write the generalization as well. That's one. Let's just write the generalization. T to the power n ut. Okay, that's going to be 1 by s to the power n, not s to the power n, s to the power n plus 1. And here I have a gamma function and gamma n. Gamma n. So again, you can understand gamma functions, right? So gamma function for integers. So if n is an integer, rather natural number, then gamma n is just n minus 1 factorial. Okay. So that's it, and you understand this. Any confusion there so far? And gamma 1 is of course 0 factorial. Gonna be 1. All right. So you have, for example, if I have power 1 here, so I would have gamma 1. Gamma 1 is 0 factorial. Okay. So gamma 1 is 0 factorial, so that's 1 divided by s to the power 2. Okay. Similarly, if I have 2 here, I would have gamma 2. Gamma 2 is 2 times 1. Gamma 2 is 1 gamma 2 is the n minus 1 here. Okay. So n minus 1 factorial. Just hold on for a second. Did I write it wrong? Here 0 factorial for 2, that's going to be gamma n plus 1. Just hold on. Yes. That's going to be n plus 1 factorial. You are right. So this is going to be n factorial, and for n to be n being an integer, otherwise it's going to be gamma n plus 1. Just write it that way. Okay, so gamma n plus 1, gamma n plus 1 is just n factorial. Yeah, so that's fine, right? For integers. And why am I writing gamma function? Because gamma function exists for non-integer values of n as well. Okay, so n could be a fraction really, and that's a very big discussion we cannot afford to do right now. So these are few standard results. Okay, now of course let's talk about a few standard properties. So we of course talked about the property of linearity. We know that it's a linear operation. We talked about the derivative property, rather I would say time derivative property, where we stated that of course if we know that the Laplace transform of xt is xs, then we say the Laplace transform of x dot t is xs minus x0. Okay, sxs minus x0. So essentially s times n. So under zero initial conditions, Laplace transform of the nth derivative of any signal is going to be s to the power n xs. Okay, now of course there will be so many terms here, but since we are assuming zero initial conditions, those terms are going to be 0. Okay, so that's a nth derivative. So assuming zero initial conditions. And many of the derivations, I mean most of the derivations would be very similar to the derivations we did for Fourier transform. We did complete derivations for all of the properties for Fourier transform, and many of the derivations will be very similar to what we did for Fourier transform. Okay, so let's talk about a few of them. For example, let's talk about the time shift property. Okay, I'm going to derive this at least. Time shift property and frequency shift property, for example. Okay, so what we are looking for is the Laplace transform of xt minus a. Okay, so when this signal is shifted a bit, okay, in the to the right or to the left, depending on whether a is positive or negative respectively. Okay, so we want to calculate the Laplace transform of this. Okay, so if we calculate the Laplace transform of this, we can say that by definition this is going to be, of course we are assuming causal signals, right? We are assuming causal signals, and we are going to use that definition here. Okay, so we are assuming causal signals. Okay, but maybe we are going to take the full definition, and let's apply that. Maybe that will be easier for us to see. Okay, so sorry, xt minus a we have here, and then we have e to the power minus xt dt, and here what we need to do, we need to do a substitution, and not a very difficult substitution at that. Okay, what we need to do is to replace t minus a with something like maybe z, and then of course we have dt as equal to dz. And thinking about the limits, we can say that here when we have t and z, and t varies from negative infinity to positive infinity, when that happens, we can see that a does not have any effect, because this is a, what should I say, a finite number, finite quantity. So when t is negative infinity, z is negative infinity. When t is positive infinity, z is positive infinity. So the limits do not change, and as such we have this definition. So this is becoming minus infinity to plus infinity, so limits did not change, and this is becoming xz. Okay, and e to the power minus, now instead of t I would have to write z plus a, right? Z plus a. So I would write, maybe here, not here. So I would write some minus infinity to plus infinity. So this is going to be x of z e to the power minus s, and that's going to be z plus a dt. All right, and then we can actually split this exponential properly. We can say this is going to be xz times e to the power minus sz times e to the power minus sa dt. Notice that we are integrating with respect to t, so anything that does not have t in it can be treated as a constant as far as this integration is concerned. So this can actually go outside, this entire term can go outside, and with that we would have this integration. So we would actually have this e to the power minus sa brought outside, and that's going to be xz e to the power minus sz. So not dt, sorry, I'm sorry about that. This is going to be dz. Yeah, thank you for correcting it. This is going to be dz. And you see, this is the very definition of Laplace transform, because we can now do a trivial substitution. Okay, trivial substitution, and substitute z with any other name, because this is kind of a definite integral with respect to z. After all, after doing this integration, z will not remain. Okay, we would have to put the limits, right? So this is, we can actually do a trivial substitution and say this is e to the power minus sa, integration from negative infinity to positive infinity, and say we can say xt e to the power minus st dt. We just replace the name here. This is a trivial substitution. We are familiar with this kind of shenanigans, right? So this is e to the power minus sa times xs, because this is the very Laplace transform of the original signal. So with that being said, we can now actually say that we know, rather we can say that if the Laplace transform of xt is xs, then the Laplace transform of a shifted version of this is going to be e to the power minus sa times xs. That's called the time shifting property. Okay. So we're going to need these properties, so keep that in mind. All right. So let's talk about the frequency shift property. Right. The question that we are asking, that if we know that the Laplace transform of xt is xs, we are looking for that thing for which the Laplace transform is x s minus t. Okay, the frequency got changed, so the Laplace transform itself got changed. We can use the same definition, okay, and from there we can actually show you that this is nothing but the Laplace transform of e to the power at times xt. So if we know that the Laplace transform of xt is xs, then Laplace transform e to the power at xt will be x of s minus t. This can be very easily proved by the definition of inverse Laplace transform. You can put the definition of inverse Laplace transform, or you can actually use the definition of Laplace transform and directly integrate this. Won't be a problem. Do you want me to show this? Do you want me to prove this, or can we skip this proof? Because I think this is quite obvious. Okay, just let me know if you want me to actually prove this. Then we want to do the time derivative property. Oh, we did the time derivative property. We want to do the frequency derivative property. So you want me to prove this? Actually, you want me to prove this since, okay, fine. So we can actually very easily do this. We are calculating the Laplace transform of e to the power at xt, and that's going to be, by definition, this integration. Once again, we are using the very full definition. Okay, so e to the power at xt e to the power minus st dt, and from there we can actually combine these exponentials. It's going to be this xt e to the power minus, we can say s minus a t dt. You see, we combined it and took a minus sign outside, so it became minus a. And now it's time for a substitution once again. So we are going to substitute s minus a. Okay, we're going to substitute s minus a with something like, just hold on, s minus a, yeah, not a problem. So we're going to substitute s minus a with a certain quantity here. So s minus a with something like p. Okay, we can write that. So this is going to be very trivial here. We do not need to do any differentiation of any differentiation of that to calculate the differentials whatsoever. So we can actually write down that this is going to be something like this: xt e to the power minus pt dt. Okay, okay, and that's not a problem, I hope. Now notice that if it was s, this would be simply xs by definition, right? If this was x s, this would be just xs. That's the definition of Laplace transform. But if this is something like p, which we just defined here, this is going to be x of p, because ultimately that is what how we define. It's defined, right? But what is p? P is s minus a. So this is x of s minus a. This is a very simple proof. Okay. So that's how we actually get the property. Not a very difficult thing at all. Okay, we again proved the time derivative property earlier because we needed that the most. And then we are going to talk about the frequency derivative property right now. So let's talk about the frequency derivative property. And the objective is, once again, and these properties are very similar to the, what should I say, the Fourier transform properties. Very similar in nature. Okay. And in fact, so similar, in fact, in some cases, you can just take the Fourier transform property and replace j omega with s, and you would get the Laplace transform property corresponding to, right? So these are so similar, in fact. So here we are talking about the frequency derivative property. Once again, we are looking for that signal. We are looking for that signal. We don't know what it is yet, for which the Laplace transform is the derivative of the actual Laplace transform. So we are saying that the Laplace transform of xt is, once again, xs. We want to calculate that signal for which the Laplace transform is this derivative of this. Okay, derivative of this. Now, of course, we can actually approach this problem in many different ways, but the standard way would be to actually, once again, to use the very definition of Laplace transform. Okay, so once again, we know that the Laplace transform any signal xt is defined as, Laplace transform of that is defined as, so let's say xs is defined as this integration. Just keep in mind, while proving all this, we are using the full definition, because it should be true for the full definition of Laplace transform. For our course, or at least for control system engineering in analog sense, we only have causal signals and causal systems. That's why we can truncate the lower limit to 0. Okay. Yeah, S is frequency. S is frequency. That's a very good question. I'm going to explain. We're going to have a complete 1 hour discussion, full 1 hour length discussion on S. Okay, this variable S. So don't worry about that. I haven't yet mentioned the different things, the nature of S, what kind of quantity this S is. So far, assume it's a complex quantity. Okay, that's it. So far, because we are going to have a complete full length discussion on S itself. Okay. Because that is something you need to have a good idea on. All right. So this is going to be xt e to the power minus st dt. That's the very definition of Laplace. Let's apply a derivative here. So if we differentiate this, we see, of course, differentiating with respect to, yeah, fantastic observation that S is definitely a complex frequency quantity. Now, what is the complex frequency? We understand only real frequencies. Okay? What is the complex frequency? What are different parts of it? We are going to have a complete discussion on that, because unless we have a complete discussion on that, there are many things about a system which I cannot talk about, especially stability. Okay, we are going to talk about all that, so don't worry. Okay, so now let's differentiate this. So with respect to S, assuming that T is a constant, we are essentially partially differentiating this. Just keep in mind that we are assuming T to be a constant, so we are just calculating that. So that's going to be this derivative on this integration. Now, there was a lawyer back in the 17th century, okay, and 16th and 17th century. His name was Leibniz, okay, Gottfried Leibniz. And you might have heard of his name. because all these symbols in calculus that we are using, not from Newton, even though Newton is credited usually as the creator of calculus, okay, but the way we write the different structures and different things, the way we use the symbols like this integration symbol, the sigma symbol, all these symbols, dt, etc., all these symbols came through a lawyer, Leibniz. Okay, so again, there is a rule by Leibniz in which we can actually bring this integration inside. Okay, we do this thing so trivially that we don't even think about it, whether that this dt is not a fact. Your teacher, your mathematics teacher, if he or she was good enough, would probably have told you that you write, when you were students, you were told that you write something like this, dy dx, and your mathematics teacher probably told you not to call it dy by dx. He or she probably told you call it dy dx, okay, not dy by dx, okay. But later on, maybe he or she told you that if you have a dx, you can cancel it out, you can just write dy. So this thing, this dy dx, which is not supposed to be a fraction, sometimes is treated as a fraction. Okay, there are so many mysterious things in mathematics, and I cannot even fathom telling you how it happens, really. Just hold on. Alright, so this thing that is not supposed to be a fraction is sometimes treated as a fraction, and this is, in mathematics, nothing is ad hoc. Okay, in some situations this thing appears as a function or behaves like a fraction, and sometimes it does not. So yeah, there are so many trivial things that we assume or take for granted, but that are not so trivial, mathematically speaking. We can't even fathom to derive that thing here. Okay, all right, just per se we can actually bring this differentiation inside. Okay, bring this differentiation inside, because this is not happening with respect to t, this integration is happening with respect to t. We can bring this differentiation inside. Not a difficult proposition to do. Okay, so what we are having is that the derivative of xs is going to be this integration from negative infinity to positive infinity, and this is going to be the derivative of this whole thing. But since this is irrespective of s and this is also irrespective of s, the derivative is not going to affect any of those quantities. It is only going to affect this quantity because the derivative is happening with respect to s. So I'm going to have xt and the derivative of this quantity. So of course the derivative of that quantity is going to be minus t. Let me just write down that derivative. This is going to be ddt of e to the power minus st and then dt. Not a problem. So this is going to be the derivative. Let's put that. So derivative of e to the power minus st with respect to sorry, not ddt. What am I writing? It's going to be dds. Derivative of this e to the power minus st with respect to s. That way, it's going to be xt times minus t times e to the power minus st, and then obviously dt. And then we can actually see that this t cannot be brought outside because this is a function of t, right? So this cannot be brought outside. So what we are saying is that this is equal to this integration from negative infinity to positive infinity minus t times xt, okay, minus t times xt and times e to the power minus st dt. So what is it? By definition, this is the Laplace transform of this quantity, right? This is the Laplace transform of this quantity. So we can say that this is the Laplace transform of minus t times xt. So that way we can now say that this is minus t times xt, for which the Laplace transform. So if we calculate the Laplace transform of minus t times xt, this is going to become the derivative of xs, right? In other words, since this is Laplace transform with a linear operation, we can bring the minus sign to the other side. We can bring the minus sign to the other side, and let's say this is equal to minus of. Same thing, right? I believe you agree with me. All right. So this is something we can readily see here. So that is called the frequency derivative property. So we are going to actually use all of these properties to actually figure a few things out. So there is a corollary of that. Corollary means a proper extension of a theorem. Okay. So the same thing is when we were talking about the Laplace transform of something like this, we can actually see that the derivative property can be extended further. Okay, so this is going to be minus 1 whole to the power n plus 1. Okay, nth derivative of xs. This can be extended very easily. You can actually do a second derivative on this thing, on this thing, and you can actually see this for yourself. Let me just make sure that I have written this correctly. Oh no, not correctly. I have written this incorrectly once again. So if this is 1, then this is going to be first derivative. When this is 2, this is going to be second derivative. Okay, when this is 1, this is supposed to be, just hold on. When this is 1, this is supposed to be first derivative. 2, the second derivative, right? Yeah. And for first derivative, that's going to take a minus sign. For second derivative, yeah, I think this is the correct explanation. Yeah, this is, you can call it the multiplication by t property, but the proper name is a frequency derivative property. Okay, a frequency derivative property. All right. You can actually do a second derivative and see that this is going to be t square xt, the Laplace transform of t square xt. Third derivative would be minus t cube xt, Laplace transform of minus t cube xt, and so on and so forth. This is the proper corollary of that. Okay, so these are the properties of Laplace transform that we actually use. Now, why on earth we need these properties to actually deal with things? Because we can actually simplify our calculation much easily with these properties. Okay, at least with these properties. There are a few more properties. Oh, is that so? Because we actually derived, I just mentioned properly, right? I just mentioned that if we differentiate it once more with respect to x, what are we going to get? You are going to get another minus t out of this. Okay, if you differentiate this once more, you're going to get another minus t out of this, right? So that's going to be t square, positive t square. And that's how, for having a power 2 here, I'm going to have a t square and second derivative here. So essentially, this is going to be 1, okay, and second derivative. Similarly, if you do a third derivative, you see that you are going to have minus t minus t minus t thrice multiplied. That's going to be minus t cube. Okay. Third derivative denoting minus t cube here, minus t cube xt. So third derivative of xs gives you, so comes from the Laplace transform of minus t cube xt. So essentially minus t cube xt, and you can see that this is actually matching up with this. And using induction, you can actually induct it for the nth order derivative. You can directly differentiate it in number of times, not a problem. Okay, so I believe that's understandable. So that's why we did not derive. Yeah, it is going to apply for any function as long as it is differentiable endlessly. Okay, as long as it is differentiable endlessly, it's going to work. Okay, so we have derived a few properties, and we are left with 3 important properties: the convolution property, and the final value theorem, and the initial value theorem. Okay, some of you are actually still confused about what I am saying. Let me say, if I differentiate this n number of times, nth order derivative. So notice if you have any confusion here. So I'm doing a derivative with this n number of times. Not a problem, I hope. Okay. So in that case, this derivative, when done n number of times, would bring this minus t outside n number of times. So I'm going to have minus t whole to the power n here. Okay. So this derivative will actually bring minus t outside n number of times, right? So that way I'm going to have something like this. Then I'm going to have something like this. But what is this quantity? Here you can see I can actually bring this, write this as, see, this minus t whole to the power n can be written as minus 1 whole to the power n times t to the power n. So this is minus 1 whole to the power n Laplace transform of t to the power n ut. All right. So that way we can now say that the minus 1 whole to the power n, okay, times Laplace transform of t to the power n xt is going to be the nth derivative of xs, right? And since minus 1 whole to the power n is just minus 1 plus 1 minus 1 plus 1 depending on the its value, you can see that this is going to be brought here, and this becomes something like 1 divided by minus 1 whole to the power n. But 1 divided by minus 1 whole to the power n is still minus 1 whole to the power n. Why is it so? Because you can actually very easily verify that for yourself, because this is going to be minus 1 whole to the power n minus 1 whole to the power n. Because if I write this, this has to be true. Okay. And this is in fact true because this is minus 1 whole to the power 2n. Okay. And 2n is always an even number. Always an even number. So minus 1 raised to an even power is always equal to 1. So this is always true. So 1 by minus 1 to the power n is equal to 1 to the power n minus 1 to the power n. So we can actually write this. I hope this worked, right? So that's again the standard definition. There are 3 more things that I need to discuss, which I am not going to do today because that will be discussed in the proper context. Okay. The 3 things are the convolution property, the initial value theorem, and the final value theorem. We are going to discuss this. These are very important properties. We are going to discuss this in the proper context in the next class. Okay. So far we have learned a few properties. So what can we do with these properties? For example, we can actually go back to the few things we wrote earlier. Okay. Let's take this very simple example. Let's talk about ut, or maybe not ut. Let's talk about ut. Okay. Let's see what we can do with this. So we know that the Laplace transform of ut is 1 by s, not a problem. So question is, what is the Laplace transform of e to the power minus at, or say e to the power at ut? Now we can of course start from scratch and integrate this and figure out the result, but we can actually apply one of the properties, which is the frequency shift property. It says if I am aware of the Laplace transform of xt, if I am aware of the Laplace transform of xt, then we can actually calculate the Laplace transform of e to the power at xt, and that's going to be x of s minus a. So whatever was the function here, replace the s with s minus a. That's going to be 1 by s minus a, and that is something we can derive directly by integration. Another example, we know that the Laplace transform of sine at ut is a by s square plus a square. So with that context, we can say that the Laplace transform of e to the power bt, say for example, e to the power bt sine at ut. Here, what am I have to do? So this is like xt, and this is xs. Okay, so we are going to once again apply the frequency shift property. We are going to see that okay, I am multiplying this with e to the power something like at or bt. So all I have to do is in this answer, I have to replace all the s with s minus b, and if I do that, that's gonna work. This was s square plus a square, and if I replace all the s with s minus b, and that's gonna happen. That is the answer. So we can actually, instead of doing cumbersome calculations, we can actually very easily figure this thing out. All right. Similarly, since we know this, we can calculate the Laplace transform of t times sine at ut. Okay, and what would that be? That would be the minus time derivative, frequency derivative of this quantity. Okay, this quantity, and let's do that for our example's sake. So we're going to differentiate this, and this is again a function like this. So this is going to be something like a derivative of 1 by x. Okay, so you know, so for example, so this is like 1 by fx, right? So what kind of result is this? So this is going to be minus 1 by fx whole square, and the derivative of. So that's the chain rule, right? That's the chain rule of derivative. You know that. So when we differentiate this here, so we say this is going to be minus a will come outside first of all. So minus a will come outside. I'm going to consider this to be a constant like that. So 1 like that. So this is going to be 1 by s square plus a square whole square. And then of course we have to differentiate whatever was down below. That's going to be 2s. So this is going to be, okay, there is a minus sign and this already got a minus sign. So that way it becomes a plus. That's going to be 2as divided by s square plus a square. So actually without calculating much of anything, we can see that we can actually calculate the Laplace transform of some complicated functions. Okay. Do you have any confusion with this? Alright. Just for the sake of another example, we can have Laplace transform of something like t e to the power bt sine at ut. Okay, so that's gonna be something you see that we know the Laplace transform of this as this, and multiplying a t here, if we calculate the Laplace transform, that's gonna be, there are so many fairy people today. That's gonna be this thing, the derivative of this. Now, of course, once again we can actually differentiate this very easily. Okay, we can so bring this minus a outside, and here it becomes plus if we differentiate this. So this becomes 1 by s minus b whole square plus a square, a whole square of that, and 2s. No, the derivative of this, that's gonna be 2s minus b. So the answer becomes 2s minus b divided by, sorry, 2a times s minus b divided by s minus b whole square plus a square whole square. So that's it, right? So not a problem again, once again. So we knew the Laplace transform of this to be this. So we knew that the Laplace transform of this was this. And then we applied the frequency derivative problem. But we can actually approach this problem in a completely different way. We can approach this problem in a completely different way. Let's see. We knew that the, see, we can write this as this, something like, so this is e to the power bt times t sine at ut, right? And we know that the Laplace transform of this quantity, we just derived it moments ago, right? We know the Laplace transform of this quantity is this, 2as by s square plus a square whole square. So we know that Laplace transform of this quantity that I have represented in green is 2as by s square plus a square whole square, which we derived like this, right? A moment ago. The Laplace transform of this. Then now we can actually apply the frequency shift property. Frequency shift property, because this is like xt and this is your xs. Okay. And so we can actually use the frequency shift property. Okay. So we just know that the Laplace transform of this is this. So we can actually copy this, paste this here, and say the Laplace transform of this times e to the power bt. All I have to do is to replace all the s with s minus b. Okay, replace all the s with s minus b. So this s is going to be replaced by s minus b, and here also this s is going to be replaced by s minus b. And as such, if I do that, you see this is going to be s minus b whole square. So you see that it wasn't a problem either. So, and the results are matching up. Okay. So we can have multiple approaches in solving a particular problem. But the thing is, if you apply the approaches consistently, you get consistent and correct results. So there are several ways in which you can approach a particular. Any confusion so far? Now, the rather important way in which you apply this Laplace transform is through apply these properties is through inverse Laplace transform. Believe it or not. The idea is that we are solving differential equations, and in order to solve the differential equations, we are first applying the Laplace transform. So that converts the differential equation into an algebraic equation. We solve it algebraically, and then we are getting an algebraic result, but it is in the Laplace transformed form. Then what we do is we take the inverse Laplace transform to get back to the time functions, time domain. Okay. So the point being, we apply inverse Laplace transforms all the time. So our objective often is to actually use these ideas that we derived to actually calculate the inverse Laplace transform of many different signals, for example. Okay. So that's going to be kind of the objective. But in order to do that, we need to use something called partial fractions. Okay, partial fractions. Partial fractions will be your friend throughout your inverse Laplace transform journey. Okay, so whenever you need to calculate inverse Laplace transform, you need, for the most of the time, you need partial fraction expansions. So what you do, if you are given a certain functions for which you need to calculate the inverse Laplace transform, you need to figure out a way in which you can think of it as the Laplace transform of something, and then you just write down that something. Okay, for example, if I now ask you, okay, calculate the inverse Laplace transform of something like this. Say, for example, I'm just completely writing something random from my mind. Okay, I'm asking you to calculate the inverse Laplace transform of this. Now, this might seem pretty weird, and you can always use Python to calculate this, and Python won't take a lot of time to calculate this. I mean, less amount of time than you would probably take to calculate this. But how do you approach such a problem? Okay, you want to calculate the inverse Laplace transform of something like this. The approach would be to convert it into a form that adheres to something we already know, that appears like the Laplace transform of something we can relate to, or something we already know. Is that understandable, or is that very difficult to take? I think this is understandable, right? So what we might think is that, okay, the denominator is looking somewhat like what we just have here. The denominator is something like what we just have here, something like this quantity, right? So let's try to express the denominator in that form, something like this: s minus b whole square plus a square, right? So denominator kind of looks like that. So let's try to represent it this way. So let's forget the Laplace inverse symbol, and let's express this in a slightly suitable way. So this is the ratio of two polynomials we have here. So keep the denominator, not 2a, 2s. Keep the numerator intact. So this is 2s plus 3. And for the denominator, let's call this s square plus 8s. Now 8s can be assumed to be something like 2 times s times 4. So if we want to complete a full square, yeah, we sometimes break it in partial fractions, sometimes we don't. Okay, our objective is to, in any way possible, our objective is to actually convert it into known forms, or standard forms. Okay, that's 8s. So I need to have a 4 square here to complete the square here, and that's gonna leave us with something like, so for example, we are supposed to have a 13, then we subtract 4 square. Not a problem, right? So you can see that we added up 4 square here, subtracted up 4 square here, and this is just 8. It's for you to see what I'm going to do. All right. So now we can actually express the numerator as whatever it was, 2s plus 3, and divided by, so here we have s plus 4 whole square plus 13 minus 16. So instead of having plus here, I have minus 3, right? Okay, fine. So minus 3 is like minus root 3 whole square, but it is not exactly matching up with this result. I mean, we wanted to have something like this, but we unfortunately don't have something like this. Let me recall that we also have a few other information. What about this? Just hold on. All right. So you recall that we had a function that kind of looked like this sine hyperbolic function. Okay, sine hyperbolic function and this cos hyperbolic function. Notice this. Let me just bring it here. Bring them here. You now have to recall things. And so you have to be very proficient in Laplace transform in order to do inverse Laplace transform. So recall the Laplace transform of the sine hyperbolic at. Let's hold on once again. Right. So we know that the Laplace transform of the sine hyperbolic at ut, that's gonna be that was a divided by s square minus a square, right? So it is like that. So of course the Laplace transform of e to the power bt sine hyperbolic at ut, so that was going to be a by s minus b whole square minus a square. So now see, it is kind of matching up with this. Okay, it is kind of matching up with this, and so does for the cos hyperbolic. Let us just say okay, so the cos hyperbolic function. So okay, cos hyperbolic function. So this is going this was going to be s here, and just like that here, in order to calculate e to the power bt times cos hyperbolic at ut, the Laplace transform of that. So all the s must be replaced here. All the s must be replaced by s minus b. So that's going to be s minus b. Right. Now you do notice that this is kind of a combination of these two type of quantities. Here the denominator has something like s minus b minus a square, s minus b whole square minus a square, and it's kind of matching up with that. You see, I can say this is like s minus b whole square, and this is minus a square, right? So we are just assuming that b is like minus 4 and a is like root 3. Is that something we can assume, or is there any difficulty understanding it? Right? We can actually assume something like that. Okay. So now once again, I told you have to be very proficient in Laplace transforms in order to be able to do anything with inverse Laplace transforms. All right. So with that being said, now we can actually split this, whatever ratio we had there, we can actually split this into two of these. So we can say 2s divided by s plus 4 whole square minus root 3 whole square, and then plus 3 divided by, so I have s plus 4 whole square minus root 3 whole square. Okay. And now of course we can, instead of writing s plus 4 whatever, we can actually now look at this very carefully and look at this portion here. Rather instead of writing this, let's look at this very carefully. So we have 2s, something like that. Okay. Notice very carefully at this one first, because we need to have some understanding of that. Okay. So if on the numerator I have a s here, so this is kind of supposed to look somewhat like this. So this is going to be s minus b whole square and minus a whole square, and on the numerator I have an s, right? I have an s. Now the thing is I can have an s, but thing is, since I have s minus b here, okay, since I am dealing with that kind of a thing, I need to also have s minus b here. I need to also have s minus b. So technically speaking, this was supposed to be 2 times s minus b, which is s plus 4 here as well. This was supposed to be something like that. If this is something like that, then of course I can bring the 2 outside. Okay, be happy with that. And now this is like s minus b once again. That would be s minus b divided by s square, s minus b whole square minus a square. This will perfectly match up with this function, right? This will perfectly match up with this function. Okay, and of course I have a 2 outside. So what we are saying is that I want this matching up to happen. I want this matching up to happen, and whatever here I don't bother about that. So I want this matching up to happen. So what happened here? I had 2s plus 3. So can I not write it as, instead of writing 2s plus 3, can I write it as 2s plus 8 minus 5? Yes, I can. 2s plus 8 minus 5. And this 2s plus 8 was brought into one of the fractions. So 2s plus 8 was brought into this fraction, and this minus 5 will be brought into that one. That way, so the partial fraction expansion is perfect for our particular D here. So how are we dealing with this? We are assuming that this is like s minus b whole square minus a square, and this is s minus b, and this 2 is just there. Okay, okay, let's just keep that first. Okay, this 2 is just there. So again, since it's a linear operation, those can be avoided. So let's just keep that in mind. And what about this one? The other one kind of looks like this. So this is like s minus b whole square minus a square, and here I was supposed to have an a here. I was supposed to have an a here, which is a constant, but I don't have that. So a is supposed to be root 3. I don't have that. Instead I have minus 5. So what can I do? I can bring that minus 5 here. I was supposed to have a root 3. So let's write root 3. Why not? But I had a minus 5. So what am I going to do? I'm going to write the minus 5 here. Not a problem. But I have to take care of this root 3. How do I take care of that root 3? All I need to do, divide that by root 3. Now I have successfully taken care of this root 3, and this minus 5 is still there. Now this is in the form that this is like a divided by s minus b whole square minus a square, and this is in the form of a plus s plus b divided by s plus b whole square minus a square, and this 2 is of course there. So let's bring this 2 outside. Okay, so once we have that simplification, now we can actually think about this as the Laplace transform of something we apparently know. So therefore we can say the Laplace transform, the inverse Laplace transform of what we had, this thing. The inverse Laplace transform of this thing is nothing but yeah. So we can now say this inverse Laplace transform is nothing but the inverse Laplace transform these two things, which will need more space to fit in. Yeah. So that's the inverse Laplace transform of this thing, but we individually know what these things are Laplace transforms of. So we know that this is the Laplace transform of 2. It came from this, right? So again, once again, let me remind you, this was s minus b whole square minus a square s minus b. Okay, so this came from the sine, this came from e to the power minus 4t, cos hyperbolic root 3 t ut. Okay. Okay, sine hyperbolic, the h goes here, okay, with the name. And now this one is minus 5 by root 3 is going to be e to the power minus 4t sine hyperbolic root 3 t. Yeah. So one of you got already? Yes, you got the correct one, almost the correct one, right? Yeah, the correct one. Now, of course, you can take this e to the power minus 4t common out of this whole thing, and I can actually simplify. So let me just make this smaller, this entire the collection thing. And that way, this is nice. So this would be simply, you can actually deal with these numbers separately, or you can forget that. So this is going to be e to the power minus 4t times 2 cos hyperbolic root 3t minus 5 by root 3 sine hyperbolic root 3t, and of course the whole thing has a ut inside. So it is again telling you that it is coming from a causal signal. So that's how you deal with inverse Laplace transform problems. You do not try to do direct integrations on this, but let me tell you, if you knew complex integration, or if I teach you complex integration and how to deal with that very definition of inverse Laplace transform, in my opinion, this problem would be easier to solve using that complex integration, using the very definition of inverse Laplace transform. So if you knew how to calculate this integral for this sort of problems, so if you knew how to calculate this integral, okay, for this sort of problems, it is often easier to deal with this using that particular integral. But if you know how to do that complex integration, but if you want to learn that particular type of complex integration, which is usable for, very much usable for inverse Laplace transforms, then I can arrange an additional class for you specifically to teach you that part. Okay, how to deal with, how to calculate inverse Laplace transform directly from that definition. Okay, using complex integration. Otherwise, you can always think about this particular standard way in which you try to separate it or try to do some manipulation so that the function appears as the Laplace transform of something standard, something well known. Then you can proceed from there. But if you know how to calculate residue integrals, how to apply Cauchy's integral theorem, then you can actually calculate that integration. And in my personal opinion, it is often easier to apply that particular integral. And that is exactly what the computer programs also do. The computer programs do not deal with this sort of cumbersome manual process. Okay, the computer programs will always think about doing the complex integration because it is easier and more systematic in nature. And often, in many complicated problems, that complex integration will be easier, okay, compared to this kind of thinking process. Nonetheless, whatever floats your boat here, whatever you like, you can do. But if you are interested in that particular, say I might take a consensus right now. Are you interested in having an additional class where we are going to study that particular complex integration? This will help you in your mathematics classes regarding the preparation of your mathematics parts as well. So are you interested in that, or can I just skip that over? I'm equally happy skipping that over as well. So please tell me if you are interested in talking about that, or you can just skip it. All right. As expected, that is not going to be a mandatory class in any shape or form. This will be only for the interested people. If those who are interested can join that particular discussion. So we're going to have a discussion where we discuss how to do this inverse Laplace transform using this complex integration. Let me tell you, for simple cases, don't ever try to apply that integration. That will make things complicated unnecessarily. But for complicated situations, for example, like this sort of problems, I really feel you people should know how to actually do that complex integration for this type of problems. Okay. And let me tell you, 100% know that nobody taught you that in particular to this compensation to this inverse Laplace transform scenario. But in any case, that is going to be the end of today's discussion. We can do a lot more, and there are three properties once again to repeat. There are three properties: the initial value theorem, the final value theorem, and the convolution theorem regarding Laplace transform. That we are going to study next in the proper formal class. But we are going to arrange one additional class where we deal with inverse Laplace transforms directly with the very definition of the inverse Laplace transform. And I assure you that that class is going to be pretty interesting. And this has direct implication in control system. I really don't know why people don't teach you this thing, why it is not in the syllabus per se. Really, it has very direct complications. And yes, of course, regarding what S is, we are going to discuss that once we complete the discussion on Laplace transform. So we are going to complete the discussion on Laplace transform, and the moment we jump into discussing systems back again, we would have a long discussion, don't worry, long comprehensive discussion on S. Okay, and let me make one thing very clear here. If you don't understand what this S is, the entire concept of control systems would be like a very foggy mathematical mess for you. So unless you understand that S as a quantity, what that S actually means, you won't understand complex. You won't understand control systems. Okay, so we are going to make sure that you understand that. With that being said, this is the end of today's discussion. If you have any query, feel free to ask at this point. Otherwise, we're just going to end the discussion. So thank you once again for being here and so patiently waiting. The handouts will be available in the video description and also in your Google Classroom. I'll just wait for a few more minutes so that you might ask a question. Alright, so it seems like you have no more questions. So we're going to end the discussion at this point. Thank you very much. I will see you in the next one. Okay, once one of you asked for the, I'm going to, okay, remember that. I have to download it and repack it and upload it once again. So that's a cumbersome process. A few gigabytes have to be downloaded and then uploaded once again. And then I can share you a link. So I'll do that, don't worry. I'll see you in the next one. Thank you.